So we are talking about this 1 degree of freedom robot arm, that arm that you want it to rotate a certain angle, and it rotates that much. Last time we talked about its modeling. It's just a simple inertia rotated by a motor that is underneath. So the inertia has a transfer function of 1 over Js squared, J being the polar moment of inertia. And the motor has might have a first order transfer function, but usually motors are fast. So we assume that it's simply a gain, Km. So the transfer function between the voltage and the angle theta is Km over Js squared. Okay. Then we have a controller. The feedback system is as follows. You want a first certain angle of rotation, and then let's say 90 degrees. You want your arm to rotate like 90 degrees, and the control system makes it do that using feedback. Okay, it feeds back the actual theta, compares with the reference theta, generates the error, and the controller generates the voltage that drives the motor. This is the command following case. Then you have the disturbance rejection case, in which you don't want to follow a certain command. That is, the arm stays as it is like this, but then a disturbance comes and hits the arm. The arm has to come back to its original position. The input is the disturbance. This is the input, okay? This is the disturbance. The reference is 0. You don't want the reference value to change. We want to eliminate the effect of the disturbance. Now, the last time we just looked at the steady state error case, and with proportional control. Okay, we assume that the controller is a simple gain like this. This is proportional control. Today we will extend this a little bit. We will change the controller. We will see that how this proportional controller is limited and why we have to introduce more complicated controllers. Okay, now for the steady state error, we will, as you remember from last time, we look at command following. This is command following. Okay. And as you might remember from last time, we found that the system type is 2. So for command following, the system gives steady state error for parabolic inputs. But for example, for ramp input, it gives 0 steady state error. For step inputs, it gives 0 steady state error. It gives steady state error only for parabolic inputs, so system type is 2. It has 2 free integrators. 2 free integrators comes from the fact that it is a free inertia. The system has a free inertia. But on the other hand, for a disturbance, if you find try to find the disturbance, let's say, steady state error and system type for the disturbance, you find that the system type for the disturbance is unfortunately 0, which means that the system will give you a steady state error for a step disturbance, which is not good actually. Even if you have a step, the system cannot recover from a step disturbance. Okay, so much for step disturbance.
Hocam,
yes.
RAM is something we define while we talking about this section, right? Because I couldn't find anything in previous chapters we covered.
Well, RAM input is just an input that grows up over the time. Okay.
Okay. Okay then.
Linear input that grows over the time. So we were talking about the proportional control or P control, meaning P meaning proportional. This thing is now R of S feedback. The controller is simply some Kp, and this our system is Km over Js squared. This is theta, and this is the feedback, okay? So P control, and we are looking at the command following. You want it to rotate a certain amount, and the system rotates that amount. So for this system, the closed loop transfer function Q of S, which is theta of S over R of S, is this thing multiplied K times G. If this is C of S, if this is G of S, okay. As you might remember, this is Cg divided by 1 plus Cg, which will be the following: Kp Km over Js squared divided by plus over Js squared. If you combine the terms, you are going to get Kp Km over Js squared plus Kp Km. Okay. You can call this Kp Km as K. This thing is K, so that you simplify T of S to be K over, let's say, Js squared plus K. So you can even write this as K over J divided by S squared plus K over J. Okay. Now, this is as you might see, this is a system that has no damping term. It is undamped. There is no S term. S term introduces damping here. So it's a second order system. Its natural frequency is K over J, and its damping ratio is 0. Okay. If you have, let's say, if R of S is 90 degrees, you want the arm to rotate 90 degrees arbitrarily, what you are going to get will be the following. This is 90 degrees, let's say. The arm is going to do the following motion. I cannot draw it very well. Actually, I will show this on MATLAB. So it will oscillate around here. And I lost it. So on. So what it does is it just goes back and forth like this and never settles down. So there is not enough damping. So the problem is there is, as I have said, no damping. And this is not good. Okay? Because it never settles down at 90 degrees. Instead, oscillates between 0 and 180 degrees, actually. This is the time. Let me illustrate this by using actually octave. Let's do this. How do I do it? Let's stop sharing and share the screen, the real screen. Okay, you see it now, right? The octave.
Yes, hocam.
We have to load the control toolbox, but no. Okay, PK. So we load the control thing. Now, our system, as you might remember, the arm is the transfer function of the numerator being kpkm. Let's say, sorry, 1, 0, 0. So the arm transfer function is 1 over s squared. Actually, it is some k over js squared, but we assume that k over this km over j, we assume it to be 0. Sorry, 1. Km over j is assumed to be 1 here. We can arbitrarily assume that. And let's say that our kp, the proportional controller term, it's again arbitrary. I tried this, it works, so we will assume that this is 2. Okay. In this case, the closed loop transfer function, T being the feedback of, okay, we can do that. Kp times the arm with unity feedback. Okay, so it is 2 over s squared over 2 will be our closed loop transfer function. We will look at the step response of this closed loop transfer function. So as I told you, it is oscillating between 1 and 2. We can increase this time a little bit. Let's say, let's make it, how much was it? It is 10. 10 is not very much, so let's set it up to 50 the time. So you see it keeps on oscillating as expected because it's undamped. Okay, there is no damping here. You would ask it to oscillate, settle around at the 1 value. We said 90 degrees, but if you really want 90, you can just say 90 times the step of this. Okay. It didn't work. You have to say step, I guess, or something like 90 times. So this is, between, it has to settle at 90 degrees, as you see, but it doesn't. Anyway, this is too much. So what do? We have to do something else. We have to add damping to the system. Now, the way to add damping to the system is use PD control. What is PD control? Proportional and derivative control. Okay, this is proportional. This D is derivative. So the C of S now is Kp plus Kd times an S. Okay, S term corresponds to derivative, as you might remember. Okay, now theta of S over R of S now is, again, it is GC over 1 plus GC. Instead of Kp, we added this extra term. This S term is an extra here. So we will have the following. Km Kp plus Kds divided by Js squared. 1 plus this thing Km Kp plus Kds Kds divided by Js squared. If you simplify it, you get Km KDS plus KMKP divided by JS squared plus KMKDS plus KMKP. Now this term is important. This is a S term. This is the damping term. You add damping to your system so that your system is going to go and become damped. Okay. On the other hand, there is a zero is introduced to your closed loop system, but it affects the transient response, but it doesn't affect the steady state error or stability. You have introduced damping, so let's look at the MATLAB thing. Now, let's say that our controller C of S is transfer function of, let's say, 2, 2, and 1. So you see that 2S is the derivative term, and 2 is itself is the proportional term. Okay, so our controller is this now. So T is now the feedback of arm times the controller with unity feedback. Okay, as you see, now the system has a derivative term like 2S here in the denominator. This is the closed loop transfer function. We can look at its step response. Step of T, if you will say that. You see, the response has some overshoot, but it settles at the value of 1. This is a unit step response. So we want it to settle at the value of 1, and it does settle at the value of 1. It does because actually you have system type is 2. You have 2 free integrators. So it's no problem. That is, you have, with command following, you can easily remove the steady state error without oscillations. PD control is enough for command following. That is the result, okay? So, as we said, for step input, even if you have a ramp input, a growing input, you would have 0 steady state error. So for command following, PD control is okay. We see that the result, the step response would be something like this, as I have told you. As we see, if this is 90 degrees, the response will be something like this, quite nice, okay? With PD control. This is, as I said, for the command following. Now let's look at disturbance rejection. This is also important. Now the disturbance rejection case is, as you might remember, is the following. The R value is not important here. R of S is 0, but there is a disturbance on the system. There is a controller. So there is a disturbance W of S plus, this is minus, this is plus, but this is Km over Js squared, as you remember, feedback, like this. This is theta. So the arm is disturbed by an external force or a torque. Disturbance. You suddenly hit the arm, let's say, and you want it to come back to its original position. We found that actually the system type, the last time we found that the system type for disturbance is 0. Okay, it cannot even reject a step disturbance. Okay, let's try first the C of S equals Kp, the proportional control. Well, proportional control as you might remember, we are looking at the disturbance transfer function, Tw of S, okay? And this will be G of S over 1 plus G of S, C of S. Actually, it might even be a minus. Anyway, remember the following. We can draw this picture like this. Since this is 0, we can draw this in a more simplified way like this. This is W of S, okay? This is the length, Km over Js squared. This is theta. This is equivalent. This system. If R of S is 0, this is what we have. We have a feedback system with controller in the feedback, and the closed transfer function of that system will be like this: G of S over 1 plus G of S. 1 plus G of S. G of S.
Hocam, this is valid if we have R of S is equal to 0, right?
Yes, exactly. Because we have eliminated R, this block this circle can be removed from here. Since this is not here, instead I have put C of S here. So this Tw of S, if you compute it for proportional control, it's going to be Km over Js squared plus Kp Km. Km being the motor transfer function. So this is the disturbance transfer function. So the system type, as we have said, is 0, but here again we have no damping again. Let's look at the step response of this system now again. And let's close this thing. This is gone. Now here the arm is the sting. The controllers Kp is here. It's still 2. Okay. Now the Tw is the feedback connection of arm and Kp, if I'm not wrong. Yeah, this is how it should be. Okay, because Kp is in the feedback now. If we now look at the step response of this system, step of Tw. Okay. Now, first of all, the Tw, the response of Tw, let's make it a little bit larger. Let's say let's go to 50 or something. The response has to go to 0 eventually, but it doesn't. It oscillates. Even if you use PD control, this won't be well, the oscillation will be gone, but still there will be some steady state error. Let's try that. Here it is both oscillatory and it doesn't settle down at a certain value. The value it will settle down is positive actually. Let's say, okay, this is C. C was the PD control, as you might remember. So this is the continuous time model. If you look at the step response of this, 50 is too much, let's make it 20. Well, this is, it might look like good, but this is the responses. This is the disturbance response. What you should have is something like this, okay, coming back to its original position. So the with no damping, you have the following response. This is P control. And with PD control, I'm sorry, you have the following response. This is PD control. And what you should have, what you really want, is this. Okay? Eventually, the response should be going to 0, but it doesn't. This is 1. You should be rejecting the disturbance. This is the desired response. So that's to be expected because the system type is 0. Even for a step disturbance, you get a steady state error. Okay? And the damping term does not really influence the steady state error. So even if you're introducing damping, with PD control, with D control, let's say, does not eliminate steady state error. All this is steady state error, as you know. This is steady state error. Or the middle of this is the steady state error. Okay. So what should we do? We have to have, as you might remember, have 3 S terms, okay? So introduce, let's say, integral control, which is P plus I plus D. So this is proportional. This is derivative, as we know. And this is the integral action now. The integral control is as follows. The controller now is the following. The proportional term, just a single. The integral term, Ki over S. You know, over S means an integration, okay? Plus Kd times S. So this is P, this is I, and this is the D term. This can be...
Can you explain where this come from?
What comes from?
Hocam, is this an equation like Kp, Ki, and Kd are the constants?
In the beginning, we started with Kp, only we had a constant, okay?
Yes.
Then we introduced the S term, which is the derivative term. Now we introduce another term, Ki over S.
So they are constants, right? Ki, kd, kp.
Ki and kd are constants, yes.
Thank you hocam.
I will explain PID control better the next time. This is just an introduction. You might not be able to understand it, but I'm just trying to, introduce it here. If you equate the numerators and denominators, you will have KPS plus KI over S here. Okay. This is, but as you see, you have in the controller, you have a free S term. And the system type actually for disturbance, because of this free S term, is going to be 0. Okay, sorry, 1. If you make this analysis, the system type with PID control for disturbance W. Well, if you do it, let's do it. CW is, as we know, is G over 1 plus CC, which is Km over JS squared, as you might remember. 1 plus Km over JS squared. The PID, which is this thing, KDS squared plus KPS SKI divided by S. Okay. Okay, if you solve it, you will get KMS. You have this free S term, JS cubed plus KMKD S squared plus KMKPS.
Hocam biraz yukarı çekebilir misiniz acaba?
Yukarı dediğiniz böyle mi?
Ha, evet hocam, okuyamadık da tam. Aynen hocam.
Okay, so this is the disturbance transfer function. For step disturbance, W of S is 1 over S, okay? So the steady state error is the limit as S goes from final value theorem, S times T double of S times 1 over S. 1 over S is the W. So these terms go away. So it is the limit S goes to 0 of S times TW KMS KS cubed plus all these things from here. Okay, I'll just quote. I don't want to write them again. You can just put them here. Times 1 over S. You see these S's cancel, but you have this free S term here. And then this, you are taking a limit going to 0. This goes to 0. So the steady state error for step disturbance with integral control is indeed 0. And we will show this by using this, what was it? Okay, this was the disturbance. So let's modify our controller. C of S, C is equal to transfer function of 2, 2, 2, let's say 1, 0. This is the PID controller transfer function. 2 are the coefficients. This is the KD, this is K P, and this is KI. I arbitrarily selected these values. The selecting these values is another matter which we will be dealing later on. But I'll just show you, in order to get a good response, you have to select these parameters correctly, but that's another matter. So we will say that the TW, again, is the feedback connection of R, and A should be capital, and C. You see, now we have a third order system, and there is an S in the numerator. That makes the big difference. Okay. Now you will look at the step response of TW, and you see that the step response indeed goes to 0, and the disturbance gets rejected. That's the important thing. Okay. So as we look at it, if we plot the response here, what you have will be something like this. This is T. This is theta. If there is a torque disturbance on the system, it gets rejected. So the PID controller, PID rejects the step disturbance, whereas PD doesn't. Okay. PD controller does not. On the other hand, we can look at the PID response for a command following. I'm not going to derive for, I'll just show it here. T is equal to, let's say, feedback of G times C. Yeah. Now we are looking at the forward. And in the feedback, there is 1. This is the transfer function between theta and R. Okay. Not, there is no, it's not G, it was the R. Okay, so this is the transfer function. If you look at the step response of the system, T, you see that the system goes to, if you want to rotate 1 degree or 90 degrees, it just rotates that much. Actually, we can just put T and TW together, if you like, 2 responses in the same time. This is too big. The blue one is the command following, and the red one is the disturbance rejection, as you see. Okay. So this system with this PID controller can follow the commands like this and reject the disturbances. There are 2 different cases, of course, but they can, in a real system, they can occur simultaneously at the same time. But you see that the PID controller, at least for the step input, does a good job. On the other hand, the transient response here is not very good. That is, there is kind of too much oscillations, but that is because we didn't really select the parameters of the controller accurately, not very well. They are not very well, but we don't care at this point. So I tried to introduce the concept of steady state error with disturbance rejection, with command following, and also the PD control and PID control.
Hujam, sorry to interrupt, but is the top graph, so the top graph is the PD control and the bottom one is the PID?
They are both PID. These are both PID controls. This is...
Okay. So then what's the difference between the 2 of them?
Okay, I'll explain. Let's see if I can write it down here. This is PID. This is command following, okay? Where W of S is 0. Actually, I don't know if this is necessary, but I'm just checking whether I can do it. And this is this thing is disturbance rejection. Where R of S is 0. Okay. Two different cases, as you see. Could I answer your question?
Yes, Hocam, thank you.
Okay. As a matter of fact, we can be a little bit fancy and try to paste it here. Okay, something like this. All right, that's all for today. If you don't have any other questions.
Hocam, I have a question for the quiz. Which topics are included, hocam?
Let me just stop the recording.